Yeah, hello everybody. My name is Franz Vaupel. I'm from Kiel University, and it gives me great pleasure to introduce Rainer Adelung today. Our Vice President, Eckhard Quandt, who wanted to do the introduction, is unfortunately not available. Yeah, Rainer got his PhD in 2001 from the physics department in Kiel. Then he joined my group. I was really very happy about that. And in my group, he got his, what we call in Germany, habilitation. That's a kind of license to become professor, which you generally need in Germany. After that, he got a prestigious Heisenberg professorship, and then he got a call from the Technical University of Munich. And after that, he became full professor at Kiel University in material science. Rainer did fascinating work in many fields. He mostly works on functional nanomaterials, and his main activity is in the field of aeromaterials. According to Nature, Rainer is among the top 10 cited scientists at our huge university, and he's also among the top 10 in terms of grants. And I don't want to go into details concerning all his achievements. To me, Rainer, it feels like I don't know, every month or so you come up with a new fascinating application of aeromaterials. And today you will present us a new fascinating application. Aeromaterials, as Rainer will convince us, are materials with zero heat capacity, and they have very interesting applications in the field of actuators, and infrared mirrors. And I think you will also talk about some other aspects. Yeah, Rainer, I'm really looking forward to your presentation.
Thank you very much for this overkind introduction. So I can blame my group for all the productivity. So that's not me. There was two little corrections. So it was still, 2000 December when I made my PhD. And we talked.
I got it from your CV in the internet, Rainer.
Okay, then I have to see the source, and that's a problem. And it was, of course, Hamburg, not Munich.
Right, Hamburg.
Yeah. Okay. So this is also wrong. What you see here, the slide, because this was an introductory slide from last time when I had the pleasure, 11 months. We just discussed this 11 months ago to discuss this topic about the aeromaterials. So this is now kind of the second part. So you see here change now to 21, and it's about materials without heat capacities. So it's about this fascinating properties with exposing aeromaterials to temperature. And it was very interesting. Last time after the talk, we had quite some discussion, and that was very nice. And there was from Shashank Priya a very good question about if these materials could be also used for thermoacoustics. And indeed, we had a publication in preparation, which was almost ready to submit. We had submitted a patent already, and he was absolutely right that this stuff is possible to be utilized in this manner. And we make now some joint research. So I'm very happy that he received some of our material, and his group is very experienced in this field, of course, and others as well. And so it's very nice to work together and making there some progress in this field. Yeah. So short topic. First, how to build an aeromaterial for those who were not available 11 months ago. Then a little bit about the unique properties of aeromaterial, where are they special, what's special about them, and so that's the idea about this. And then coming on properties and applications of these materials where it says without heat capacity. So here you see some images from the talk. So here from synthesis to the material, but very important are these two people. So Fabian Schütt, he's doing a habilitation now in my group, and he's leading a team of researchers, and it's mainly in his group where all this progress was done, and mainly by the PhD student Florian Rasch, and but he graduated now at the end of the last year, and now he's gone. But he's also main person in the lab, beside of course Fabian, who's coordinating these things, and still also sometimes working in the lab and bringing the ideas together and creating this new material and application, very important. So, well, I think you've seen this image many times. So for this seminar, so that's Kiel. So we are located here in the Faculty of Engineering, how we call it, which is an area here. Here's a big shipyard. So if you see, weather looks approximately similar, and then you see kind of from the through the window here these big portal cranes, which are here employed to build the ships. Okay, so first, before I can talk about the Aeromaterials, I wanted to talk about the synthesis of the Aeromaterials. And the synthesis contains material where we did a lot of research on zinc oxide. So zinc oxide is a material you shouldn't do research on because there's too much research on zinc oxide. So there are literally 100,000 publications on zinc oxide. And if you go in the last 20 years, and still like 50,000. So it's extreme amount of literature, and it seems to be that almost everything is done on zinc oxide. So if we see it from a non-emotional perspective, then we see that zinc oxide is 2,6 semiconductor. It's a versite structured crystal material. So it provides on the macroscopic scale transparent hexagonal crystals. If you grind and every transparent material, you get a scattering of light at the edges, and then you get white powder, white appearing powder. So if you grind glass, usually you can find the same. So it's used almost forever as a white pigment for wall paints, for example. But it has also, and this is also almost forever, at least already 2,000 years ago in history, used as in medical treatments. Nowadays, it's still used, for example, in dental treatments. If you have the unpleasant event of a root channel treatment, then they put you in some zinc oxide. It's a biomaterial, and as you can make a transparent conductive material out of it, you might use it as transparent conductive oxide for LEDs, thin film transistor displays, solar cells, and so on. It's piezoelectric, it's photocatalytic, and what was important for us here when we started with this research, it's very simple to do nanostructure formation, because the material is highly polar. If you see this versite structure here, you have zinc planes and you have oxygen planes. And if you have now some free zinc, it has a high affinity to the oxygen. So as soon as here's some zinc available, new oxygen comes on the surface, and that grows in this direction very rapidly. So it basically shoots out here along the C-axis. And that's also the secret how this crystal is grown here. If we magnify it, so you see here, first view, no crystal, you see a microparticle which has kind of hairs on it. So this was a zinc microparticle, and was just some nanoscopic gold just done by wet chemical synthesis deposited on top of that. And then the whole thing was heated in an oven under ambient conditions. And so then indeed these hairs shoot out, and these are containing out of zinc oxide. And this is single crystalline zinc oxide, which is grown under this mainly kinetic dominated conditions, and is growing here very rapidly out. And this material is flexible because it's so thin. And this was very inspiring those days to my group and myself. So what to do with it? So ideas were, what if you can make a material kind of consisting only out of this hairy stuff here and these microparticles in between, and then you have to guide, for example, currents also through these hairs and so on. And we try to scale it up with an embarrassing simple synthesis. So the idea is if you have some zinc particles and you have some sacrificial material in terms of oxidation, some organic stuff, like for example, polyvinyl butyral, which is a polymer which is extremely cheap stuff and is somewhere produced in chemistry. I don't know very exactly, and is considered kind of like a garbage. So we get this for free since 15 years, I would guess, 14 years, something like that, almost since the beginning of the group, because it's so cheap that they always laugh if you want to have a few kilograms. So that's very nice. So I thank the support on PVB. However, if you have this stuff here and you put the whole thing into a very simple oven, for example, a muffle type of oven, which is open to atmosphere, then the following happens. The PVB gets burned and catches up all the oxygen around from the atmosphere. So for that, you have for a while then control over the oxygen content, and the air is depleted on oxygen. This gives time till the zinc particles can melt or kind of form some thin oxide layer on top and develop a molten core, which then cracks maybe through this thin oxide film on the surface and forms then these spikes. In reality, this looks like this. For example, if you zoom in more and more, then you see indeed there are a lot of particle and spikes. That's not the only thing which happens with the zinc oxide synthesis. There was like another accident happen. You might know if you take a look, for example, at the NFL or something like that, and you have a pizza in the oven, and you forget about the pizza, and then you open the oven rapidly, then you add a lot of oxygen to this depleted atmosphere, and then maybe some reaction like this might take your pizza up all to the kind of ceiling here, roof, to the top of the room, and deposits there some gray flakes. With the zinc oxide, you can do similar. If you put this mixture into a ceramic boat, if you heat up the whole thing under oxygen depleted conditions, after some time, there's developing an upstream of the zinc, which is evaporated. Then the zinc can crystallize like snowflakes together now with the oxygen, which it finds around after all this, for example, PVB material is completely oxidized. And then you can put it on a catcher substrate or directly harvest it out of a large crucible. So here you see how it looks in the oven if you take a look into that. So you see here a kind of a slow reaction process, and all this foam is here coming from this PVB. And afterwards, it looks like this. So you have here, this white powdery substance in there. And depending on the condition, you can grow even larger crystals like you see them here. Actually, I hope you can see my pointer. Let us switch to the laser pointer. So yeah, you see here even millimeter long crystals. These are then single crystals. And there's a company, Firestone, and for medical reasons, they have upscaled this in a clean room. And you can see you can make really a lot of this material. So now we have this type of material, and we do a lot of research on that. It's fascinating if you're taking a look into this. Other than these other particles, you have here a tetrapodal shape. Yeah. So you have like a surface and a center, and then you have like 4 arms out of zinc oxide, C-oriented crystals. And these are kind of growing together. You can see this, for example, here on this larger view. Or if you're changing the condition, it could be that also this connection in between are very tiny. So this goes to the nanoscale, approximately diameter here in this image at this position here, 1 micrometer. So it's all kind of interconnected stuff. You could also take this powder and compress it and sinter it later on a little bit more together if you want to control the density, for example. Well, we are doing a hell lot of research with all this stuff because it's a relatively simple and cheap way to get nanostructures, and with nanostructures you can do a lot. For example, building very fast sensors. Imagine you have some chemical species there, On top, you can do supercapacitors and so on. Has also some biomedical activities, and you can employ, and so this was what I showed last time, but this is now new stuff since last time. You can employ this as a template and, for example, make porous materials where you have channels in between. So you put some material around your tetrapods, and then you dissolve these zinc oxide tetrapods. And that is one plus point, which is at the same time also a minus point. So negative side and positive comes together. It's very easy to etch away zinc oxide with moderate pH. So pH 5 will already do the trick. So if you eat this zinc oxide, for example, here like this amount of white powder, if it's in the stomach, it's completely decomposed and it gives you zinc. And we all need like 13 milligram zinc, I think, a day. So yeah, you can use this, for example, to create, use it as template to create kind of tunnel networks for different purposes, but also you can employ it in medical stuff. So if you're interested in this, that is the guy who invented this flame transport synthesis in my group, Yogendra Kumar Mishra, who had successfully done his habilitation, and 2 years ago he became professor in Denmark at the SDU University, and he wrote a very nice review, which is still okay, I hope, even though it's 3 years old, for about this tetrapod materials. And this starts with a warning, so there's too much of zinc oxide if you go on the Web of Science. So that means that even not Yogendra is an expert in zinc oxide. There's no expert in zinc oxide because there's too much literature nobody can read. However, that's the point in time where we have to get rid of the zinc oxide. And one way was done together with the people from TUHH. There's Professor Karl Schulte. He's expert in carbon CVD. He was doing a lot of research, for example, with carbon nanotubes and later on with graphene. And he, together with Matthias Mecklenburg, who was PhD student in his group, was trying to grow some carbon nanotubes on that. However, there was an interesting experiment which failed, but which created kind of like images like that. So there was a leakage of hydrogen during this CVD process, carbon CVD process. So they were depositing carbon on this tetrapodal material, but at the same time, it was etched away by hydrogen. And that was a very lucky finding. And Matthias Mecklenburg very systematically tried to find out what was happening. And it cost him over a month, but he was a very precise guy. So he found at least that it's the right concentration of hydrogen you have to add. Because then you obtain a kind of hollow network of these tetrapodal shaped objects. And so this makes the material extremely lightweight. So if you kind of convert it completely, then you have a material consisting out of these tetrapods. Here we see some end tetrapods, but it's all connected due to the synthesis. And where you have a kind of wall thickness here of just a few nanometers, can be grown up to 50 nanometers, but usually you are very happy with 10 to 20 nanometers wall thickness. At the same time, the arm diameter is more on the micro scale. So it's like half a micron to a few microns usually. And then it's all interconnected to macroscopic dimensions. You see this here. So this is, I think, what is it? Our usual is 1 centimeter, so it's 10 millimeters across. So, but what you do here is you make a material which is extremely lightweight. So the record we manufactured was 0.18 milligram per cubic centimeter. So if you compare it to normal materials, so polymer has a gram per centimeter approximately if it's lighter than water, a little below. And if you go then 3 orders of magnitude down, then you're like around a milligram per cubic centimeter. You're at the density of gases. So the material you put into the gas here is then even lighter than the gas around. So it's like adding only 0.18 milligram per cubic centimeter to this 1 milligram per cubic centimeter you have from the air around. So this is extremely lightweight. Those times it was a most lightweight framework material which was there, which was 2012. And it has other properties. It's still quite well electrically conductive, which is of importance for utilization. And it is like viscoelastic, and it has a negligible Poisson ratio. So like a sponge, maybe you know these little earplugs you can do for noise canceling in your ears. They're very soft and you can compress it. They have also no kind of Poisson ratio, so you can just compress them without making them broader, because basically there's air around. And that was very interesting that this material appeared to be viscoelastic, at least that it's elastic, because it's consisting out of graphite, and that's not very elastic. So, and this secret could be revealed. Another property is that the material is very, let's say withstands high forces, very robust. So if we take a stress test now to this aero material, we can see this in this movie. This is a charged stick, and you see here now how these little pieces are dancing up and down. So what they are doing is the following. So this is just an insulating table. You have here this aero material, which is conductive. This plastic stick was rubbed with some other polymer, and so there's some electrostatic charges. And what's happening now is that this conductive material is polarized and attracted and jumps to the stick, picks up some charges, is of course by the same charges expelled here, thrown away, and hits the table. At the table, it gives a little bit table to charges to the insulating table, and is repelled there as well. So repulsive force, and it jumps around till it loses all its charge, and then it comes eventually again at the stick. But at the first, you saw this in real time, not in slow motion like now, and you saw it was very fast. So by acceleration, you cannot break this material. I have here some material, for example. So if I accelerate it like mad also, there's nothing which is going to happen, because the material has basically no weight. So that makes it quite interesting, for example, for space applications. And there's another video, I skip here now due to the sake of time. So I showed this also last time. You have here 2 plates, and you can press it completely flat together, and you can open it up. And it's glued here at the top and at the bottom, so that it's kind of opened up again, because otherwise it would behave viscoelastic. And how's that? So we could understand that. That should be on the next slide. It has this very special structure. So this was done basically together with Nicola Pugno and Donald Ertz, where Raimund Meyer was doing measurements. He had a very cool machine there with 4 atomic force microscopy arms, with which he could grab an individual tetrapod on the micro and nano scale and do some mechanics on that. And he found out what you see here in this sequence of images. So if you bend the material, then you see there's a certain bending angle under which it buckles. And then you can fold it up straight again. And this buckling is here simulated by Nicola Pugno. And you can see here that you can come to a certain bending angle, and that then there's no additional momentum necessary, but it just bends further and further. And this is what you can see here, for example, in this video. Hope that it's working. Okay, so here you see the arm, the cantilever arm, it's bending more and more dramatic. So you have here a side view on that. You see, and there will be one point where now this arm goes forward and it's doing this buckling. Should be visible pretty soon. Yeah, here now. It jumps forward and pushes, and now you can retreat with the cantilever. You see it's less bended. And then you can see later on it flips back to its original shape. And the viscoelasticity comes if there are many of these arms kind of folded together, for example, like this, then there's of course van der Waals forces in between them, and you have basically to peel them off. And so this is taking time. This is where you consume the time, the viscoelasticity. Yeah, so this recipe works for this Aeromaterials quite well, for this, how we called it, aero graphite. You can also make aero silicon, for example, by depositing with a CVD process, or ALD would be more elegant in order to have conformal coating. Or if you heard the talk from Franz Vaupel with ICVD, then you have also a nice coating of the material with polymer. And if you etch it away, then you have some kind of functionality, which could be quite nice, because it's like that you take a thin film and fold it into the third dimension. And with this, you create here a network again, and this can be employed as sensor. And for example, for acetone gas response, it can be utilized. This is work from Oleg Lupan, who always likes to take the stuff into a part, putting it onto a microchip, and using the FIP to mount the contacts to see how the individual conductivities are and how this is reacting to acetone vapor. However, also the total network is kind of working as acetone sensor, but in this way you can control how much stuff you have switched in parallel and which is serial. Okay, so now coming to another variant, which I showed briefly last time, and which I need also as introduction, which is Aeroboronite. Fabian Schütt, I mentioned him, he's leading this team who's doing the Aeromaterials in my group. And he found a funny way to do hexagonal boron nitride. Hexagonal boron nitride is nice material because of one of these layered materials with which you can do a lot. And so he used some ammonia deposited on hot zinc oxide. And here you see, by the way, some zinc oxide fabricated to certain shapes. This is done by taking the powder, compress it a little bit, and resintering it. And if you come then with ammonia there, and at the same time evaporating boron in a CVD reactor, then the ammonia might be reduced on the hot zinc oxide and takes away some of the oxygen with the hydrogen as water. And at the same time, then you have some radical nitrogen, which is then very happy to form together with the boron on this kind of surface, which is now on the zinc oxide, coated with a film of molten zinc, because the oxygen is taken away by the hydrogen, to react to boron nitride. And you can see what's going to happen here. So this zinc oxide template is getting kind of almost transparent, blurry. It is an aero material like the aero graphite, but now you're employing a material which has a very wide band gap, like 6 electron volts or something. And so you can basically look through this light. However, there's a certain chance that the light is scattered at some of these tubes, and so therefore you cannot look through that, only if at the thin part here at the sides. And this reveals, for example, some of the properties you can you have here with the what's special about Aeromaterials. Here in this case, it's the ability of light scattering. If you're coming with a laser in here, then the laser light is scattered. So maybe I can sketch it here. So if you come to the Aeroboronite with, for example, 3 different laser colors, then the laser hits here somewhere sooner or later an arm of a tetrapod, and there the light is scattered. And even, if it hits the same place, if you have tiny kind of changes in the angle where it's hit it, and that might be also to thermal vibrations already the case inside of this aero material, then it takes, after a few collisions, a completely different path. I suppose also that quantum mechanics is involved if individual photons are hitting these hexagonal structures, which are only a few nanometers thick, then near field effects kick in, and I would not wonder if it would scatter all the time at it, even though if you do the same experiment to a different angle. However, there's some of these confusion principles, I would say, and then all the light is scattered all over this sample. And if you add then green, red, and blue light, you get at the end some white light out, as you see here. Yeah, and you can tune this, you can do tunable diffusion and so on, and maybe go all the way towards Anderson localization, where the light is kind of trapped and running here around forever and coming not back. You see at least that you see their nonlinear behavior of the transmission, depending on the density. And so in this way, there's a kind of range of tunable diffusion, for example, for laser light applications. And I think that's very special only for this Aeromaterials, because it's extremely lightweight, but it's doing a kind of laser reflection where you have no speckle pattern. One problem is that laser light is so coherent, and if you want to use it for some illumination purposes, you have to despeckle it, and it loses coherence within this materials, for example. Yeah, well, for heat capacity, there you could also employ this material and try to, use it. So if you're adding certain amount of heat to a solid, then you expect the temperature increase by heat capacity times temperature. I hope I get it right direction now. And this heat capacity is depending on the mass. So if you're taking this into parts further, so this should be here capital C. This is a small c times the mass. So this is a specific heat capacity times the mass times the increase in temperature you get. And if you now take a look and solve it towards temperature increase, then you see that if you have a material which has negligible heat capacity because it has a negligible mass, it will at the same amount of energy you added, go up in temperature really drastically. And you could, for example, add this temperature from the outside, or you could use a kind of current where you're heating it, because the aero material, if it's aero graphite-like, is conductive. And then you see the mass is in the denominator. And if the mass is in the denominator, it has a drastic effect. If you would take graphite, don't know what the density is, but let's say around a gram per cubic centimeter, the Aeromaterials is around a milligram per cubic centimeter. So that means that here in this case, for example, it heats 1,000 times faster, even though if it's the same volumetric expansion, like a cubic centimeter. Yeah, because it's much more diluted. So that means that, for example, if it takes 15 to 20 minutes to come to, let's say, 400 degrees, then it would do this with the same amount of energy in a second or two. And if you can go even faster. And first, this was utilized in a collaboration with the Institute in Greifswald for plasma research. They had an infrared camera looking to aerographite, and before they had a plasma jet flame. And they were very surprised to see the mirror image of the flame inside of the aerographite. And the supposed explanation for that is that the mass is extremely lightweight, 1 milligram per cubic centimeter. There's almost no heat capacity, but inside of the aerographite on this time scale, there's also almost no heat conductivity. because these are also only arms which are connected to other arms, and it takes quite long time till the heat makes it through. So actually you can hold it in the hand, and from one side comes a burner, and at the other side you do not get burned. And it has almost no heat conductivity, so it gets, and it's almost perfect black body, because you see it's really black in the optical. And infrared emissivity is probably also 1.0, because there's kind of no other convection or heat conductivity. So that's one way of application. And then we thought about, okay, wow, we can do this maybe also electrically. And he was doing that, Fabian Schütt, together with Florian Rasch. And this was what they called electrically powered repeatable air explosions. Or we together figured out this name. And E-Pray. And the principle is the following. You have your Aeromaterial, and there's a lot of air inside. The Aeromaterial, if it's approximately 1 milligram per cubic centimeter, there's another milligram per cubic centimeter of air inside. If you put on now some Joule heating, for example, with 10 watts or something like that, then immediately this Aeromaterial gets up in milliseconds to very high temperatures. So heating rates can be up to 300,000 kelvins per second. And so it's absolutely rapid how you can heat it, for example, to 400 degrees C. And at the same time, of course, also all this air inside gets warm, because it has approximately the same heat capacity like the material around. And so now this hot air shoots out. Well, if you switch it off, then you have a cooling process, because inside you have then like bit of vacuum. You have lower pressure, and all the air kind of shoots back. This is also pretty fast. While this is a millisecond or below, this takes at least like 0.2 seconds. So it's a slow process, but incredibly fast compared to normal dense material. And for that, they did also another type of synthesis. So besides the CVD synthesis, you can also infiltrate quite nicely nanomaterials. So you see here how this zinc oxide sample is soaked now with a graphene solution, and you can do exfoliated graphene oxide, or reduced graphene oxide. This is in collaboration with the TU in Dresden. Xinglang Feng is there the professor who's the expert in creating this nice inks of graphene. And then you can dissolve the zinc oxide underneath, for example, doing critical point drying, and then you have your Aeromaterial as well, which looks then basically similar to the aero graphite, because it's aerographene, because it's graphene based. And you see here again, it's a really thin wall thickness. This is like 1 to 2 micrometers, and so this is nanometers. Okay, so that's this material, and the heating process can be figured out also thermodynamically. So you can heat it up in very short times by applying a kind of current through that. So below a millisecond, then the whole thing is hot. Next, what is happening is that all these air molecules are accelerated now thermally. They are shooting out. So you're going from this isochoric heating, the PV diagram, down now to this expansion, this adiabatic expansion, where it shoots out with interaction with the surrounding. And then it just cools back, approximately isobaric cooling, where all the air shoots in. And then you can kind of do this forever. That's why we call it E-Pray, like repeatable air explosion, electrically powered repeatable air explosion. So that's behind this funny abbreviation. Yeah, and here you see this. If you do certain power pulses, then the temperature shoots up really fast. So here the sensor starts only at 150 Kelvin around, or 120 Kelvin. So this axis is here chopped. And then it has to cool down, and then you can heat it up again, and so on and so forth. And you can see that this is very stable. So 100,000 cycles is, for example, no problem. And it depends a little bit on the materials you're employing, which maximum temperature you reach. For example, there's a exfoliated graphene or the reduced graphene oxide. The reduced graphene oxide is relatively cheap in production, but is performing here really good. Okay, so yeah, you can take here a look then at the details, what you can do within the seating and so on. And as usually in my talks, I'm running a little bit out of time. So I try to stress here only the kind of most important aspects. So one important aspect here is that you must do a reality check. Is it really a property of this Aeromaterial? You can say, yes, if you leave the zinc oxide underneath and you have only the graphene at the outside, you can still heat it up pretty fast, but not so fast like if you etched out the zinc oxide. But here it takes more than a second to cool down if the zinc oxide is in, while here you have a much more rapid cooling. And that's very important for this repeatable action. And this, is also differable from other materials. So if you have an aerogel, for example, it has a much denser structure, which is more like sheet-like, as tried to be sketched here, while the Aeromaterial is much larger and kind of the expandant with much more kind of free accessible volume than the aerogels. So the aerogels wouldn't be, even though if they're similar lightweight, be successful in this heating. And here you can see now this demonstrator as an actuator. So inside of the syringe is Aeromaterial. It's contacted here as both sides. And you can now push here a current through. So here's some nitrogen gas in there to avoid oxidation, because you go here over 400 degrees, it's approximately 1000 degrees. And you can see this here now. Yeah, you see a kind of a bright spot. It's switched periodically, and while it comes, it kind of moves the syringe up, even though this here is around a milligram. So this milligram can be also utilized now to push this 2 kilograms up. So this doesn't matter basically. Okay, it's a bit of cheating because you have the air compressed in here now, and it's acting a little bit like an air bumper. But of course, the material must withstand that, and that's no problem. So if you calculate that and compare this with other actuators, then you get here figures like that, where you see that the E-Pray is really good in terms of strain, what it can move with the hot air, and gravimetric power density. So there it can outperform many other things. And if you want to go here to high strain but high gravimetric power density, E-Pray materials, these Aeromaterials might be a good choice. So high strain and high gravimetric power densities, and pneumatics kind of on demand without any kind of little kind of electrical engine compressor and so on. And for example, here, applications in soft robotics could be done. This is a rubber membrane, which is underneath equipped with such a Aeromaterial with 2 connectors, and you see it moves up and down quite fluently by putting some power pulses in there. And this rubber material is a commercial material where you basically put this underneath, and you don't have to be afraid that it is now like 300, 400 degrees. The rubber is not melting, because the rubber has a much higher heat capacity due to more mass than the air can transport underneath. And it takes a very long time till it gets hot. And here it's approximately too much exchange with heat to the outside so that it can be applied. So, and that found the way to all kinds of demonstrators. So for example, you can pump up here these soft rubbery membranes, but you can also do like microactuators. You can also do a fluidic micropump. If you have here a valve and you put the air inside, then you can push some fluids around, or use it as an air thruster, which is, I think, shown here in this video. Yeah, come on, to switch off the laser pointer. Here we go. So you see here, this is now this fluid flow, this pump set up. And here you see the pump in action. So the pumping chamber is here on the right. And now you see sometimes really that it looks digital. So I would say it's not a stepper engine, it's a stepper pump, which always moves now with one pulse this liquid here a little bit forward. Or if you have just some air outlet, then you can kind of get air blown here against something for movement. You see this here, how it's moved forward here by the syringe outlet. Aeromaterial is again to the right. And here at a different frequency. So that's a good thing about electricity. You can switch it on and off and do it on demand, however you want to have it. Yeah. So yeah, this is another application. And I think now there's coming, yeah, even more rapidly and so on. Yeah, this micro actuator we have seen already looks a little bit like a frog. Yeah, and can be even much more rapid. Or you could use it as thermoacoustic effect, and that's something which is done in Shashank's group. And maybe you hear it now. I crank up the volume here. So that's an aero ear plug. So everything is taken out except for the aero material. And you might hear this noise here from this frequency generator. Of course, it has a different transmission line like a normal speaker. So you have to consider some things. For example, you cannot kind of create a lower density in air by moving the membrane backwards, but you can work around that. But anyway, that's really nice to work with Shashank on that. At the same time, this can be also a sensor. So the setup is here that you have the aero material here. Here's a pyrometer where you see that the temperature is decreasing drastically if you're just blowing some air at this. You see here now is coming somebody with a very sophisticated device to blow some air at it. And then you see here directly that the temperature is going down. Of course, conductivity is also going down at the same time, changing here because you have a heat-dependent conductivity. So if you use this now as a readout, then you will detect these changes. Okay, and probably you have enough now of all this aeromaterial actuator stuff and so on. So then we can also blow it up. So what's the ultimate limit? You can see this here, 500,000 Kelvin per second heating rate. You hear Fabian about the successive blown up of the aeromaterial. That's the limit. So even though the aeromaterial is very open, the air can shoot out, there's a transportation limit. And Nicola Pugno again was figuring out what is the limit and when are these individual arms are kind of blown away. Okay, I want to thank very much my very active group, especially Florian and Fabian, but many others, for example, like the guy who invented this synthesis about zinc oxide, this flame transport synthesis, and the team is much larger. Lena Saure, Mete Haug, for example, they are doing all this applications and actuators, and Mete is doing this towards biomaterials. And so conclusion, yeah, with the aeromaterials, due to the extreme properties, you can probably do some stuff. So thank you very much for your attention, and sorry for taking 5 minutes too longer.
Yeah, thank you very much, Rainer. I think everybody is convinced that I didn't promise too much. Even for the colleagues here in Kiel, it's fascinating to see how quickly you come up with new approaches. Yeah, your talk now is open for discussion. Please just use the microphone because I cannot, or maybe I can change my settings to see all of you. But anyway, just use the microphone to ask questions.
So if there are no questions, I will take the opportunity. Things that I wanted to ask you for a long time, Rainer.
Okay, here you go.
So first, like, you know, what I would call your despecular device, right? Yeah. So I think this morning, actually, not in this talk, you said you get rid of the coherence. How do you know?
Yeah, only by checking the speckle pattern, actually. So we see, depending on how dense the material is, how much despeckle we have. Mm-hmm. So if it's not too dense and too much and a small sample, then you still have some speckle contrast. And from a certain density on, you don't see visibly the speckle contrast anymore. So that's what I should say. So it's beyond kind of human vision, I would say.
You know,
of course,
we have
it might be on a much faster frequency there. Our ideas are about that, and that there's also maybe some vibration inside of the individual tubes, and that might use then to kind of enhancing this random walk. But there's a lot of research we have to do to understand it completely.
You know that we have a despeckler device, and we know we're reducing, or we're not seeing the speckle, and it's reduced by a factor of 10 to the power of 4. But I'm very sure it's still there. We just modulate it and mix it around, and then we're not seeing the speckles anymore. Yeah. So you basically have a random distribution of speckles, and then so this is our understanding. Yeah.
So it's very homogeneous, basically. So homogeneous.
Yeah, or you know, if it's it's very homogeneous. Yeah, but each path would still be there. And the second, I have 3 questions related to that. Do you have any idea about the length of the path in your material?
We calculated that, but sorry, I cannot come up with numbers. But it's more like kilometers.
Kilometers, oh.
Yes, it's fascinating. It's really a lot. So we had discussed this with a company which is also very interested in this despeckling. So there were several companies asking, and they calculated also their passes, and they saw that we are like more than a factor of 10 further than they have.
Yeah, but
we should do this together simply. If you have this and we can compare it with your despeckler.
Yeah, but then if it's kilometer, but the coherence length of your laser is probably not a kilometer, so probably it is gone.
Yeah, but I don't know. I cannot prove. So we have to see. Yeah.
And the third question that I have, but that I would have to go looking at the kilometer lengths and how that would refer to, but you know that we have a picosecond laser, so we can do time-resolved microscopy. So we can put in one pulse and see how it penetrates or expands through your material.
I didn't know that.
And that would be
fantastic, because that would be below. And we tried this with physics with Michael Bauer, and that was not successful.
But that's very similar, you know.
Yeah, wonderful.
And why wasn't it successful in this case?
Because this laser was somehow not running.
No, our laser runs.
Yeah, and this material is done by Lena Saure. And she has also another variant besides this boron nitride. She can make it also out of silicon dioxide, so meaning glass.
But the repetition rate of our laser is 50 nanoseconds.
Wow.
No, but that's a repetition rate. But so the problem, we have also a nanosecond laser. So it depends.
But you can integrate. You can kind of do one shot of.
I know, but you know, in 50 nanoseconds, you get 5. Your light does a path about 5 meters. So everything that is slower than like how light penetrates like in 5 meters, we cannot see because so probably, you know, the length is too long, but we should discuss. That would be a beautiful experiment, actually.
Yeah, one more. Yeah, it will be really interesting. So this was a way how we tried to tackle it down to see. So we could tune the density simply by compressing the material. I was here a little bit quick to that, and that is very nice because you can see it here also how gradually the laser is kind of losing intensity. But the more you compress it, the less gradient you can find till you cannot see any gradient anymore.
I can see once more the best discussions among local colleagues are stimulated by inviting them to international conferences.
Probably.
No, the other 2 questions I had on my mind for a long time, but just now listening to his talk, it came to my mind that one could even check, you know, how far it gets. At least
definitely. We have to do this. I will immediately tell Lena.
Yeah. Very good.
Ulrich, you also have a question, please.
Yeah, thank you, Rainer. It was a pleasure to listen to you again. I'm a medical person, as you know, and I'm a generalist in science especially in your science, of course. And I always ask myself whether there are applications of these wonderful devices for energy storage, which is a big problem nowadays, to store energy, for instance, electricity or some other energies, to have this in a large society. And of course, this is nanometers, and then to have a battery or a huge battery or super battery for household or for several cities or for computers. Do you see any perspective in that direction? And the other question, just to make it finish, is I understand that zinc oxide tetrapods have an antimicrobiotic action. You showed me the white powder, and it is already in use. But this is a more a chemical sort of action. Now you showed there are sort of mechanic functions you can apply. Do you have any speculation in which direction you can use such mechanic functions with these materials in medicine?
We have a kind of medicine project with this Aeromaterials. So if you see these foams, they are completely conductive and air is kind of going through. And we can make them macroscopic for filters. So together with the company Lufthansa, we are developing filters sponsored by the graphene flagship. And the idea is to use this as antiviral, very important nowadays, and antibacterial material in the filter. So if the air goes through the filter, sooner or later there will be a collision with some of these tetrapod arms, and as the usual filters is working, you will have some agglomeration of material inside of the filter. But here you can pyrolyze this filter just by pushing a current through, and then it's refurbished. So basically going to 300-400 degrees C, it's, yeah, no problem. We got from Regina Scherli some airborne bacteria and doing some tests with them. Nowadays, we also utilized, after Christina was moving out, her laboratory for some bacteria tests. And that's very encouraging because you can, after short heating pulses, completely kind of kill the bacteria. So that's, yeah, bit biological application. And indeed, we are using that stuff for batteries, but only in basic research. Sandra Hansen is working on that in my group. She's leading their bigger team building batteries, mainly from silicon anodes. And this is the best material on the anode side of a battery. And those can be coated, for example, with sulfur. And that's the cathode of the battery. And in this way, we can check how to hold the sulfur in place for these batteries. This is important for trying to avoid the sulfur loss, which you usually have in a battery. So for research, battery research, this is already there. And there's some supercapacitor research, which is, again, under Fabian Schütz's kind of domain. So having peak pulses, very fast currents. And he has there a collaboration with Valeria Nicolosi from Ireland. And she's there, I would say, the leading person in supercapacitors. And she claims that within this framework with her materials, she can get even better supercapacitors. So we will see. So for energy, it's indeed important. So you had the right kind of ideas.
Yeah. Yeah, usually we don't go much beyond 5 o'clock, but maybe if there are one or two quick questions and Rainer quick answers, then maybe we can continue. Yeah, Rainer, I have just one comment. Did you check, for instance, with Gerhard Schmidt, the frequency characteristics of your headsets?
Oh yeah, that is, yeah, with Shashank we are also doing
Okay,
that.
yeah.
So that's very simple. So you have a frequency doubling. Yeah, so if you have a sinus wave, the negative part is also just heating the material.
Right, because
so
it's power driven.
Upwards,
Yeah.
So
right.
if you want to have a good sound, one version might be to have a baseline in heating. Of the material, and then you add some more heating, so an air wave will go out, and then you cool under the already kind of given temperature, and in this way you're soaking in the air again. So then it's like a normal loudspeaker, but you have always this constant power consumption. Then you can get really also high quality sound in this trick, but the disadvantage, and that seems to be the disadvantage, is you have constant power supply.
Right.
But you can make, for example, a flat loudspeaker, like a flat screen, which you cannot do with normal magnetic loudspeakers.
Yeah, further questions. Just use the microphone. Yeah, if this is not the case, Rainer, thank you very much again for this great talk, even for us in Kiel.
Thank you very much for staying so long with me. Okay. Have a nice day.
Sadi, do you have any announcements to make?
I do not. Thank you so much for taking the time to introduce and to speak, Rainer. And again, the next pack seminar is on July 28th. And for us, it'll be 10 a.m., but for you, it would be 4.
Yes.
Thank you.
Thank you, bye, everybody.
Bye.
Thank you.
Goodbye.
Bye.
And thanks again, Rainer.
Tschüss.